servo piston moves, the inclination of the swash plate decreases, reducing the delivery flow. Next, we will explain how the regulator increases the flow rate. When the delivery pressure of the pump P1 or of a companion pump P2 decreases, or when the pilot pressure is released by the power increasing control system, the compensation rod and piston are pushed back by their springs. As the compensating rod moves, the lever rotates, moving the feedback lever, which in turn moves the spool. As a result, the pressure within the larger side of the servo piston is released through the tank port, which then moves the servo piston. As the servo piston moves, the inclination of the swash plate increases, increasing the delivery flow.
There's so many good animated things that are available to look at for demonstration purposes now. I wish this was available years ago. This one isn't necessarily for aircraft, but it covers adjustments. Realize that many of these pumps, you can adjust the compensator to a limited degree. What it does is it influences the amount of spring pressure on one side of the compensator when you do that. So it takes more system pressure to offset it. So that's how they make the adjustments.
And you have some basic knowledge about the 9, sometimes 7 pistons in the cylinder barrel that are drawing in fluid through half of the shaft rotation and expelling fluid through the other half. Let's now look at how this pump can vary its displacement, and let's look at the function of a controller mounted to this type of pump that is typically known as the pressure compensator. When you see the green highlighting appear, don't forget to have a look at the matching symbol in the upper right-hand corner of the screen. Other typical names for pressure compensator are pressure override and pressure cutoff. All of these terms describe a feature that may allow us to go without a relief valve, as is commonly found mounted to a T-fitting on the outlet line of a fixed displacement pump. Let's look at just a few common components that we will be speaking of throughout the video. The inlet line A is shown in violet, with the cylinder barrel assumed to be spinning as shown in the 3-dimensional mimic. And the pump output or discharge port is shown here at port B. This is the swash plate. There is also a very important component called the control piston, and a component known as the bias spring. The pressure compensator has an adjustment screw, a spring, and a compensator spool. The compensator has an inlet port that is monitoring the outlet pressure, as shown on this line with the jump tags labeled lowercase letter a that passes behind the volume stop screw. We will speak more about the volume stop screw to limit the pump volume output in a part 2 video. We've installed a needle valve to act as a generic hydraulic system circuit resistance. In other words, closing down on the pump's outlet line is going to allow us to build system pressure on the pump's outlet port. On the controls, we have 2 adjustment dials, one coarse adjustment and one fine adjustment, but they ultimately both control the same needle valve. Using the 2 different dials is just for teaching convenience. As you know, a needle valve typically has only one adjustment. A flow meter will indicate flow rate, and a pressure gauge will indicate system pressure. Starting out, the pump is producing 10 gallons per minute, which is its maximum value, and the system pressure is at a low value of 100 psi. The pressure indicated on the gauge is merely a measurement of hose and fitting resistance throughout the system as fluid travels back to tank. Notice on the controls that the compensator indicates a setting of 500 psi. How can we prove if that label is correct? Let's tighten the setting of the needle valve to cause greater circuit resistance. Naturally, this causes our system pressure to rise. Just after passing the 400 psi mark, we notice that the pump's pressure compensator has become active. Also notice that the swash plate is now moving, and notice that the flow meter indicates less than full value. Remember, we started out with 10 gallons per minute. As we continue to tighten the needle valve, we eventually arrive at a circuit pressure of 500 psi, and we find out that the flow meter now indicates zero flow. Naturally, there is zero flow on the pump outlet line as the needle valve has been closed completely. If this was a fixed displacement pump, a relief valve mounted to a T-fitting right near the pump outlet would have to divert the pump's flow back to tank in order to avoid a catastrophic overpressure condition. The pressure compensated pump is also referred to as a variable displacement pump. When there is no flow path, as is the case with our closed needle valve, the pump simply resizes itself to produce near zero flow. The resizing of the pump is accomplished by taking pump outlet fluid and using it to extend the control piston. When the swash plate moves towards the vertical position, the individual pumping pistons in the cylinder barrel now have a near zero stroke length. The pump is maintaining 500 psi maximum system pressure on the outlet line. In every piston pump, some fluid is leaking internally between close-fitting parts. When the swash plate is perfectly vertical, this leakage causes the system pressure to drop slightly. The spring inside the pressure compensator pushes the spool downward to the closed position. This allows the bias spring to push the swash plate back towards the maximum angle, which would increase the stroke length of the individual pumping pistons. But since the needle valve is still closed and there is no flow path available, system pressure quickly reaches the setting of the pressure compensator spring, and the control piston once again moves the swash plate towards the 0-degree angle where no pump outlet flow occurs. The action of the pressure compensator is essentially maintaining a constant pressure. If the hydraulic system requires a top system pressure of, say, 1,000 psi, we will need to adjust the pressure compensator spring. This adjustment needs to be made when there is no flow possible on the pump's outlet. In many systems, it simply requires one to stop operating the directional valves. In this system, we have a closed needle valve, so we are ready to make the adjustment. With a pressure gauge available on the pump outlet line, simply turn the adjustment screw to compress the spring until the desired maximum system pressure is reached. When we open the needle valve, pressure will fall and the pump will return to maximum displacement due to the force of the bias spring. That is the meaning of the bias spring. The bias spring means that the pump has a tendency to produce maximum flow whenever possible. As you can see, when there is an easy flow path for the pump's displacement, changing the setting of the pressure compensator spring has no impact at all on system pressure. In a real-world hydraulic system, the maximum system pressure limit would now be unknown. This could easily become a dangerous situation. The pressure compensator adjustment must be set with the pump running and when there is no system flow occurring. In this video, we have covered the basic function and adjustment of the pressure compensator. Thanks for watching.
We have hundreds of interactive resources like this live schematic.
The illustration up at the right side it's an ISO hydraulic schematic, or at least a pictorial that's given in ISO format. Eventually you're going to have an assignment, I can't remember if it's in the lecture or the lab, where you have to do a written a schematic or a system of your own design. I'd like you to use ISO symbols for it. So you can see if you had to draw out a pictorial of a hydraulic system, it's way too complex to draw the individual components out. What we use in order to simplify the operation of the description of the circuit is to use ISO symbols. This symbol with a circle with a triangle in it, that's a pump. The arrow through it indicates that it's a particular type of pump. It's a variable displacement pump. They have it controlled by a control piston. This is the pressure compensator, the symbol for it. This is really the diverter that is able to either establish flow or deliver flow back to the reservoir. The symbol for the tank is usually just a symbol like that. So, but you'll be using ISO symbols for that one written assignment. So anyway, kind of cool anyway. I've got something to show you too. I've got some animated schematics to show you operation of a simplified view of a 757. So you take a look at this. This shows you what you would have in a typical Boeing. You've got 3 independent hydraulic systems that use combinations of electrically driven pumps and engine-driven pumps, and they all work in unison to support systems that we have in the aircraft. Brakes, yaw damper, left and right aileron, alternate brakes, spoilers, rudder, elevator. A lot of things in the aircraft are hydraulically powered from multiple sources. So you can see, for example, if we're talking about the aileron, the right aileron, it receives an input from the left system hydraulics and also the center system for redundancy. If we lose either one of the pumps or both of the pumps in the center system, or we lose flow from the reservoir or availability of fluid from the reservoir, that same aileron is operable from the left system. But what I kind of wanted to show you is the operation in the event that we have a complete system failure. And this would be something like a PTU that would be incorporated in the aircraft. The PTU is, again, a combination of a pump and a hydraulic motor, and all in one component part. This would be the motor end of the PTU here, and it's connected by a common shaft to the pump side, the other side of the PTU, which is really a pump. And they're illustrating what it does on this part of the circuit. This would be the motor side of the PTU, and then the pump side of the PTU is over here. What it does is it attempts to repressurize the left hydraulic system by turning this, which is the pump, is drawing fluid from the very bottom of the reservoir below the standpipe, and it furnishes fluid to just a couple of, or at least essential parts of the circuit. And I don't know what they got. Maybe they got one with the engines that can operate. No, that's the RAD. But you can see the PTU does, in fact, kind of, it allows us so that we don't have to draw fluid from in this case, our right system. It just attempts to repressurize the left system with fluid that is provided from the level of the standpipe in the reservoir beneath the standpipe. But it'll furnish fluid, and it looks like in this case to flaps and slats, landing gear for landing gear extension, and I don't know anything else that it really attaches to. But again, for emergency extension of the landing gear. And anything else? Well, that's it for the PTU. The RAD is a little bit different. The RAD also provides an essential functions only. When it's deployed, again, it's driven by relative wind. It goes through a check valve and pretty much only to the center system. But it provides for elevator feel, it provides for the yaw dampers, stabilizer trim, right aileron, left aileron, spoilers, elevators, and rudder. And again, that's all that it'll supply to. But when they do the architecture for a particular aircraft, there's a reason why they did it. And again, sometimes it's kind of a hunt to figure out exactly what they did, but there's usually a reason behind it. But anyway, that's the rat. Okay. I don't know, some large aircraft, not all corporate aircraft have a ram rear turbine or a PTU. Usually it's going to be a commercial aircraft, airliners that have both of them and stuff. Some of these are military.
When did they start using rats?
Oh my God, that went back to I think the late 1940s, early 19. As turbine engine powered aircraft kind of came about, that was pretty much the beginning part of it. The late 1950s or so. So that's what I can show you. Hey, what I'm going to show you next, I'm going to fill up the remainder of lecture. I've got a pneumatic system VHS tape. It was originally a film strip, but it's been converted to a VHS tape. It covers a little bit on vane pumps, mostly dry vane pumps. So I'm going to show you this next. And then we'll talk about the test for next week. This goes back to probably the mid-70s or so, 1977 when they did this thing.
For centuries, man has used air as a means of power. The Dutch, for example, used windmills to reclaim much-needed land by pumping back the sea. Long before steam was harnessed as a power source, sailing ships relied upon air to open commercial sea lanes around the world. Today, in aviation, we not only use air as a means of flight, but for power to operate important instrumentation. These systems are known as pneumatic systems. They require periodic maintenance and careful adjustments to ensure efficient operation between inspections. For this reason, this specialized training program has been prepared to help you, the professional aviation maintenance technician, to better understand aircraft pneumatic systems and their components. Modern aircraft pneumatic systems evolved as a result of demands for a constant air source necessary to drive navigational, gyroscopic instruments, and many other aircraft systems. In the early days of aviation, this air source requirement was not nearly as important as it is today. The crude gyro instruments were simply spun by a stream of air flowing over buckets cut in a rotating wheel. In some models, airflow was accomplished by evacuating the gyro case by venturi tubes located on the outside of the aircraft. But when flying in adverse weather, these venturis were susceptible to icing, making them impractical for flight under conditions where these instruments were needed most. The first mechanical application of aviation pneumatics was the use of an oil-lubricated or wet pump. This unit used a small amount of engine oil, metered under engine oil pump pressure, to achieve its sealing and lubricating qualities. Once lubricated, the oil from these parts was discharged into an oil-air separator to prevent unsightly oil stains on the belly of the aircraft. This separator allowed the oil to flow back into the engine oil supply for recycling back through the pump. As the state-of-the-art in autopilots, de-icing equipment, and gyroscopic instruments advanced, an absolutely clean, oil-free air source was needed. In order to accomplish this with an oil-lubricated pump, additional oil-air separation devices were necessary, increasing the overall system weight. To avoid this problem and meet the demand for clean oil-free air, a new type of pneumatic pump, a self-lubricating dry air pump, was developed and is currently available from a number of component manufacturers. This new generation of dry air pumps eliminates the need for external oil separation devices, and rather than using steel vanes that rotate inside a cast iron cavity, these pumps employ carbon vanes sliding in a carbon rotor. These vanes wear constantly in microscopic amounts to produce the lubrication required. Many of these dry air pumps are bidirectional, meaning they can be operated either clockwise or counterclockwise. To accomplish this vane construction is much the same as an oil lubricated pump, with the vanes radiating directly from the center of the rotor. On other types of dry air pumps, the vanes are canted into the direction of rotation. This allows the use of longer vanes, which reduces tip velocity to increase their useful service life. To maintenance personnel installing unidirectional pumps, it is extremely important to match the rotational direction of the pump with that of the engine drive pad. The direction of pump rotation is determined by simply looking at rotation of the drive pad, or by viewing the pump from the anti-drive end. With this new generation of dry air pumps, aircraft owners are often able to obtain a pump service life comparable to the total life of the engine. Maintenance costs are less, and greater reliability and air safety are also achieved. However, as aircraft began to fly at higher altitudes, where the air is extremely thin, further changes in aircraft pneumatic systems are again necessary. To illustrate this, at sea level, a typical dry air vacuum pump has a compression ratio of 1.3 to 1. At 30,000 feet, however, its compression ratio is 4.5 to 1. Using the same pump, but as a pressure pump instead of a vacuum pump, its compression ratio at sea level is 1.23 to 1, as compared to 1.78 to 1 at 30,000 feet. In short, the lower compression ratio of a pump, the lower its operating temperature and wear factor. Based on this, pressure pumps at altitudes above 15,000 feet will last up to 30% longer. Since the only function of a pump is to move air, dry air pumps may be used in either vacuum or pressure systems. In both cases, the extremely close tolerances used in the manufacture of these pumps makes it imperative that oil, grease, or degreasing fluid not be allowed to enter these pumps. On vacuum installations, a polyurethane garter-type filter surrounding the regulator air inlet located out of the engine compartment prevents contamination from entering the system at this point. A central air filter, mounted on an instrument's air inlet, removes contaminants such as tobacco smoke before they can damage instruments or the pump. In pressure systems, the air comes from an area less susceptible to smoke and dirt, thus reducing the danger of contamination. These filter elements, however, should be replaced every 100 hours or as recommended by the manufacturer. After the air is regulated in a pressure system, it then passes through an inline filter that removes particles larger than 0.3 of a micron. Since the smallest object the human eye can detect is about 40 microns, this is indeed a very effective filtration system. In addition to filtration, the airflow produced by either a vacuum or pressure pump must be controlled. This is achieved by installing an adjustable flow controller. In a vacuum system, a relief valve is installed between the pump and instruments, so a constant low pressure or vacuum is maintained on the instrument side of the valve. This is accomplished by allowing filtered air to enter the system when the pressure is below that for which the valve is set. In a positive pressure system, the relief valve is located on the pump's discharge side. This maintains the proper pressure required by the instruments or other appliances. In this type of installation, air pressure from the pump acts on a preset diaphragm, opposing the force of an adjustable spring. Excess pressure beyond the regulated limits lifts the diaphragm and dumps it overboard. Another type of regulator used with dry air is the inline pressure regulator. Here, air pressure tends to seat a ball valve against the action of a spring. If the pressure rises above preset regulator limits, the regulator shuts off the line until the pressure drops. Both types of regulators operate smoothly and quietly. Some multi-engine aircraft using de-icer systems have another type of pressure regulator that constantly provides regulated air pressure for the pilot's gyro instruments. In these applications, when high pressure is demanded for de-icer boost, a solenoid valve momentarily shuts off airflow to the co-pilot's gyro, permitting the maximum volume of air to enter the de-ice system. As soon as the pressure in the boot rises to its required level and deflation occurs, this air is then redirected to the gyros. The interruption is so short, instrument operation is not affected. Two-stage pressure relief valves used by many twin-engine aircraft maintain a low pressure setting to the gyro pressure regulator. When the solenoid on the relief valve closes off the low pressure side, the pressure then rises to the level required by the de-icer boots. A second valve, the primary relief valve, maintains air pressure to the gyro instrument regulator. Generally, this is about 5 psi. When maintaining aircraft pneumatic systems, a good rule of thumb to remember is that pressure alone does not determine the speed at which the rotor of a gyro spins. This is the job of the airflow, which may be indicated by the differential pressure across the gyro. A standard suction gauge, for example, measures only the difference in air pressure inside the instrument case and the outside air. While it provides a good indication of what the regulator is doing, it tells nothing about the amount of air flowing through the instrument itself. If a filter clogs or the line from the filter to the instrument becomes pinched, the suction gauge will give no indication of trouble. In fact, the reading may be even slightly higher than normal. A standard pressure gauge will give the same misinformation. A clogged system can restrict the airflow, but as long as the regulator functions properly, an indication of sufficient pressure will be seen. The differential pressure gauge used in either a vacuum or pressure system gives total information as to the airflow through the instrument. The pressures of the instrument inlet and outlet are compared, and if the airflow is restricted into or out of the instrument, the differential pressure will be noted. Since the main function of an air pump is to move air, anything that restricts this flow of air causes the pump to work harder, generating more heat. The restricted flow also deprives the pump of the cooling air it needs, thus shortening its service life. To assure that the airflow through the system is not restricted, use only fittings and lines of the proper size and design. AN fittings are commonly used in fluid lines. However, their thick walls produce restricted bores, and the fluid flow through them must turn at right angles, creating back pressure or turbulence. The use of an AN elbow will often produce a pressure drop equivalent to 10 feet of the same size tubing. In comparison, low-loss fittings have thin walls and swept corners. This eliminates turbulence within the fitting. Used consistently, these fittings will keep pressure drops in the system to a minimum. In addition, the hose from the pump to the vacuum relief valve in a vacuum system should be no smaller than 5/8 inch inside diameter. If the gyros are connected in parallel, each gyro should have a 3/8-inch inside diameter connecting line from the central filter and to the relief valve. In a vacuum system, never use a hose less than 5/8 inch inside diameter between the pump inlet and vacuum relief valve. When driving two gyros in series, always use a 1/2 inch inside diameter hose from the relief valve to the artificial horizon first, then a 3/8 inch inside diameter hose between the artificial horizon and directional gyro. In multi-engine installations, both vacuum pumps feed into a common manifold. This manifold has two check valves connected by lines to the source indicators on the differential pressure gauge. Both pumps supply the system. However, in the event one air source fails, it will be shown by the source indicator. Movement of a large volume of air under an appreciable pressure requires a great deal of work, resulting in the generation of heat. In larger output systems, these pumps must be additionally cooled by directing a blast of air over their finned surface. In conclusion, the air used in aircraft pneumatic systems must be filtered. This air is moved by pumps and controlled by regulators. In this way, it operates our highly complicated gyroscopic instruments, autopilots, and de-icer boots to allow flight in adverse weather. Careful maintenance and inspection of these systems are important in order to achieve maximum service life and performance. The preceding presentation has been an introduction to basic aircraft pneumatic systems. Since it is your responsibility as a professional aviation maintenance technician to keep these systems at their peak operating efficiency. Part 2 of this presentation will deal with the entire pneumatic system, its maintenance, and troubleshooting. Part 1 of this presentation reviewed the various components of basic aircraft pneumatic systems. We are now ready to discuss the general requirements of the entire pneumatic system, its installation, and troubleshooting. Since the pump is the heart of a pneumatic system, we must clearly understand how it functions to service the system effectively. Often, a pump will fail because it has been overloaded or overworked, rather than through any fault of the pump itself. For this reason, air pumps are rated according to their capacity and differential pressure. No pump should ever be installed in a pneumatic system whose requirements exceed the limits of the pump. Never add equipment unless approved by the airframe or pump manufacturer for a particular installation. And do not modify any system without first determining if the total air load is within the operational capability of the pump. If pump failure should occur and replacing the pump,
Boy, that sure dates this presentation. I don't know if you've ever seen a dial telephone.
is certainly another component within the system.
We used to have a dial telephone at the hangar. I don't know if it's still there.
Yeah,
There, still there.
Rather than continually change parts, the service department of the manufacturer should be contacted immediately for a recommended course of action. Dry air pumps are precision components that must be matched to the system. To determine the right pump configuration, refer to the airframe manufacturer's parts catalog bearing in mind that often bulletins may be issued by the manufacturer to change a specific model. During installation, special care must be taken when handling the pump itself. If dropped, its carbon rotor and vanes could crack, causing the pump to seize. Caution, never return a pump to service if it has been dropped. When installing the pump, do not clamp it in a vise with the jaw across the pump body, as it could cause the carbon rotors and vanes to crack. To install the fittings in the pump, hold it in a vise across a mounting pad using either wood or soft metal jaws in the vise. Low-loss fittings are usually recommended during installation because AN fittings, with their smaller inside diameter and sharp corners around which the air must travel, have a more restricted flow. A small amount of silicone or polysulfide spray on the male threads will serve as a lubricant for installation. Anti-seize compound or Teflon tape should never be used, as a small amount could enter the pump and cause severe damage. Screw the pump fittings in until hand tight, and then with a box end wrench, tighten them until proper alignment is reached, never more than 1.5 turns beyond hand tight. Check the condition of the pump drive oil seal in the engine, and if there is any leakage, replace it. The drive end of the pump must be protected from any contaminants such as oil or solvent. A common practice in the field is to replace this seal each time the pump is replaced. Prior to installing the pump in the engine, determine if the pump will turn without binding or in a lumpy manner. Now, using a new gasket, install the pump on the drive pad, mounting it in the position that provides best clearance for the attached lines. Using the proper washers, lock washers, and nuts, torque the attached nuts uniformly from 40 to 50 inch-pounds. After the pump is installed, connect the hoses, being certain that they are perfectly clean inside, free from any oil, solvent, or foreign debris. Be sure that the hose laminations are not separated, as sections or pieces of the hose are instant death for the pump. When washing an aircraft engine down with degreasing solvent, gunk, or water, it is advisable to place a short cleaning rag over the mounting flange area, the area where the coupling is visible. This will prevent accidental forcing of the cleaning solvents or drugs into the working parts of the pump, which would cause serious damage to the carbon-moving parts. Also, if the hose has been removed from the inlet fitting, protect this opening with a plastic stop or plug to prevent foreign matter from entering the system. Operational speed is one of the factors that determines the service life of an air pump. Some engines have pump drive pads with a speed of 1.5 times faster than engine speed, while in others the speed is the same as the crankshaft. Keep in mind, the slower the pump rotation, the longer its service life will be. This is an important point to remember. Service life of a pump is directly proportionate to the load it carries. And since the technician controls the load placed on the pump, he also is responsible for the length of its service life. Another probable cause of short pump life is an overload caused by airflow obstruction. This is often due to a faulty or plugged filter within the system. In a vacuum system, replace the air filter every 500 hours or more often if the airplane is operated in extremely dusty conditions. The foam garter type filter on the vacuum regulator should be replaced every 100 hours of operation, and again, in the event of dusty conditions, more often. In a pressure system, replace the pump inlet filter each 100 hours. The 3/10 micron inline filter, located at the inlet to the gyros, should be replaced after 500 hours. In the event of pump failure in a pressure system, Be sure to replace the inline filter as well as the pump. The reason for this is the possibility that small, sharp carbon particles from the old pump could be discharged into the system, and with vibration and time, the particles could cut through the paper filter element and cause damage to the gyros. Aside from routine filter replacement, these filters should also be replaced in the event of a gyro malfunction or any indication of pressure drop on the differential pressure gauge. Keep in mind, a standard vacuum gauge cannot indicate the condition of the filter. If a pressure drop is noted or a gyro appears malfunctioning, check for a clogged filter before attempting to adjust the pressure regulator. Also, check for pinched lines or obstructions in any of the airflow lines. If a regulator adjustment to correct a pressure drop is made improperly, or an adjustment made when the real problem is due to obstructed airflow, the pump will be unnecessarily overworked and its life will be shortened. In modern pneumatic systems, both the vacuum and pressure regulators are quiet operating and trouble-free. Once they've been set, do not readjust them unless absolutely certain the regulator is at fault. To make the initial adjustment on a vacuum regulator, unlock the adjustment screw and turn it clockwise to increase the suction. Set it to the value recommended by the airframe manufacturer and relock it. When installing or troubleshooting a pressure autopilot system, such as a Britain, first set the regulator to the pressure required for the autopilot. This is usually around 5 pounds per square inch. Then, adjust the gyro instrument regulator to the required pressure. This is usually around 2.7 pounds per square inch, but always use the specifications of the airframe manufacturer. If a range of pressures is allowed, set the regulator to the lowest level. This will aid in maintaining longer service life of the pump. By using low-loss fittings throughout the system and installing only approved filters, pump life will be further increased. Never use a line with an inside diameter of less than 5/8 of an inch between the pump and the regulator. When driving 2 gyros in series, use a line no smaller than 1/2 inch in diameter connected to the artificial horizon. And if only 1 gyro is to be driven, a line no smaller than 3/8 inch should be used. The inlet and outlet lines of all instruments must be of the same size, unless you are increasing or decreasing volume from another instrument. And any hose that has become hard, has developed cracks, or starts separating should be replaced. Twin-engine aircraft use a central manifold and check valve assembly, through which both pumps are connected to the gyros. In the event of an air source failure, one of the check valves will isolate the inoperative part of the system, allowing the remaining pump to carry the load. A source indicator in the aircraft panel gauge will show a red button to indicate which source is out. Modern pneumatic systems provide the muscle for autopilots and de-icer systems, as well as the air power for the gyros. Careful maintenance of these systems will aid in preventing leaks or obstructions that could shorten the service life of the air pump. For you, the professional aviation maintenance technician, to be capable of effectively maintaining these systems, you must have an intimate knowledge of their operation. It is hoped that with the specialized aviation maintenance training program, you have gained a greater insight of the aircraft pneumatic system and its many components.
I show that to you because I like the music. I've got a test scheduled for next week. Would you like to spend a little bit of time in review? You know the difference between open center and closed center hydraulics? Which one is most commonly used today, open or closed center? For what reason?
Later.
Well, it's a difference that closed center might have, but what reasons might closed center be better suited to?
It reacts quicker and it's
Yeah,
instant.
reacts quicker, you don't have to build pressure, you're not dependent upon cutting off flow, or you don't cut off flow to one component to operate another one. Anything else? I think that's about it. So generally a little bit faster in operation because pressure is always available. The other thing is, if you look at how the selector valves are mounted with open center, if you divert flow to one actuator and make that actuator work, it's possible that you won't have any fluid available for an actuator that's in series or that's downline of it, but because the selector valves are in series with each other. No problem. What else? Anything else? If we have a electrically driven pump, we don't use a unloading valve to control the discharge of the pump. What do we use? Pressure switch. Pressure switch, that's right. So. There's a lot of different ways that we could pressurize a reservoir. And this kind of shows the reason why we pressurize a reservoir. Prevents pump cavitation. Hopefully you looked at that video that I sent you a while back. It was pretty good. It covers a little bit about cavitation. It's extremely damaging to a pump. When the vapor bubble collapses, it imparts a huge force on the component, and that's really cavitation. Cavitation is influenced by velocity and it's influenced by pressure. So if you don't have any pressure on top of the fluid going from a reservoir to a pump, or the speed of the pump is too great, it produces voids in the liquid that are essentially gaseous bubbles. And when the bubbles collapse, it causes extreme damage to the pump itself. A lot of different ways we can pressurize a reservoir. We can use bleed air that's regulated from an air pressure regulator. We could use maybe a bootstrap reservoir itself. It's got a floating piston in it. If we need a source of airflow and we don't have a turbine engine, we can have other pieces of equipment that operate off of a Venturi, either a Venturi T, a jet pump, or an aspirator. And or possibly too, we might have just a line that might be used as a vent, but it's plumbed to the inside of a pressurized aircraft. So it provides a source of air pressure on top of the fluid. So those are the methods that are generally used to provide pressurized fluid in the reservoir. Other things to prevent cavitation, I talked to you about this one today. A lot of pumps have an integral impeller in them, and it's an initial stage of push on the fluid before it gets into the heart of the pump. And then we might use on some aircraft, I think I used an example of a C-130. They've got an electrically driven pump that they use to push on the fluid from the reservoir prior to getting to the engine-driven pumps. So those are all methods of pressurization anyway. And let's see what else. You should know the functions of a reservoir, what it does. And regardless if it's pressurized and non-pressurized, the functions of it. You should also know the component parts of a reservoir, the typical component parts. You should know what else, the reason why we have a standpipe inside of it, the purpose of baffling inside of it, where a finger strainer might be mounted in the reservoir. Methods of indicating fluid quantity. You might have a dipstick, you might have a sight gauge, you might have a device called a liquidometer for indicating quantity. Liquidometer is a direct reading type of device. It's got a float with an arm on it, so as the float changes its position, the motion is transmitted to the arm, which causes a sector gear and a pinion to rotate. So that allows you to indicate the quantity that you have in the level line of the level in the reservoir. The reason why we have a check valve mounted on some vented reservoirs, and I think I point this out a lot of times during the checkout of reservoirs in the lab, that fluid flow that's trying to return to the reservoir is restricted by the filter that you might have in a vent line. So we needed an additional escape path out, so that's why we have it. If you don't have it, as a large quantity of fluid tries to get back to the reservoir, it can't. So what we want to do is we want to provide an escape path for air that would normally be trapped in the reservoir out, and we do that by means of a check valve that leads that goes out to the vent line. Temperature indication, usually done at the usually done at the inlet of the reservoir. And you know the reason why. The fluid is at its hottest point in the circuit prior to being cooled off by the reservoir. After all, the reservoir, one of its functions is to serve as a heat exchanger. So you usually find at the return line to the reservoir, that's where the temperature probe might be mounted. Also, too, the line that comes back to the reservoir for return usually is not mounted radially to the wall. It usually comes in at a tangent to the wall, and that provides for the fluid to get rid of the heat. So you know that. And accumulators, I think this is really important. Or let's go back to reservoirs too. The things that can influence the level in a reservoir. You have to kind of think for yourself, you know, why the level of a reservoir unexpectedly went to some other low point. These are the only major things that I can think of that would cause that to happen. When you have actuators that have been moved to positions other than what would be considered to be the baseline for measurement purposes of level in the reservoir, understand that many of the actuators are unbalanced. You've got a flat piston face on one side and a rod on the other. So that's it. Fluid temperature influences the level. Accumulator condition influences the level. And that's about all. I would know maybe a little bit about accumulators and some of the terminology that we use by them, some of the conventions that we have with them, so we can get there kind of quick. Different types of accumulators. Ways of checking the accumulator pre-charge pressure to verify what it is. There's really 3 different methods for doing it. What else? What's meant by the term servicing? Can we service an accumulator? Methods of, or at least what's meant when you're linking a gas charge, what it does. So you should realize when we've got a flat accumulator, that's what we usually term that. Also, too, notice that you can entrain the gas from the gas out of the accumulator into the fluid if a bladder should rupture or the diaphragm should be damaged in any way. And that'll cause erratic pressure indication. What'll happen is the gas finds its way in the pressure manifold, it begins to expand, and particularly when it gets to the bourdon tube. When it does that, it'll cause the needle of the gauge to start to sweep upscale. So as the gas begins to expand. Different types of service valve, you should know the rated pressure for each of them and how they operate. What else? Conventions for charging an accumulator. You pretty much know what that is. Always take a look in the service manual, though. I think that's kind of important. What else? With a self-displacing accumulator, the advantage maybe of having something like that in the system, it gives you the opportunity to use airframe manufacturer to use a smaller reservoir because it has a reservoir storage area. It's under low pressure. So it gives you a little bit of an advantage. But two extreme conditions or positions of the piston in a self-displacing accumulator. And accumulators, again, they don't necessarily have to be charged with gas. They just have to be a resistive force to hydraulic fluid in the pressure manifold. You might find maybe that the accumulator is a piston type where they've got a spring in it, and you might find another one that's not necessarily used in aircraft, but it's a dead weight type of accumulator. So the fluid is resist entry by means of a weight. So when we want to force fluid into the pressure manifold, the weight forces the fluid out the discharge port. Anything else?
I have a question.
Yeah.
The roll pin, just what does that do again? That roll pin inside the MX-2889.
It prevents the valve from completely being disassembled. If you were to loosen the swivel nut, it limits the travel of the swivel nut so that you can't. It's impossible. So that if there's gas behind the valve, it prevents it from becoming a missile. Some of the 6287 valves, they don't have any stop. So again, if you, in theory anyway, if you loosen the swivel nut far enough, you can cause separation of the valve. And again, if there's gas pressure behind it, maybe it'll become a missile. What else? What other things you want to talk about?
Will we have any math problems on this one?
Nothing in hydraulic theory for force area or pressure. I don't think so. But I don't think so anyway. What else? Constant displacement pumps, geared rotor and piston type pumps, also stuff on vane pumps. Do you know the difference between wet and dry pumps for vane pumps anyway? Let's see. Methods of protection for a dry pump. They usually have got a plastic coupling on the drive. The plastic coupling is designed to be frangible. It breaks at a specified torque. So they don't use a shear shaft in these types of pumps. They've just got a plastic coupling it's attached on both sides with pins. And when the coupling finally shears, usually the pump has been overloaded or it's binding internally. What else? You saw the use of low loss or swept fittings for vane pumps and the reason why. How far do you tighten those fittings?
No more than 1.5 passes.
Past
And
tight. How come?
you don't want to strip it.
What kind of threads are those? They're pipe threads. What would happen if you tighten the pipe thread too much?
You could crack.
You'll crack the casting. I've got several master cylinders out in the shop. They're perfectly fine except the casting is cracked. Somebody decided to torque on them too much and they broke them.
But how far? 1.5 times, you said?
That's the limit. Usually you tighten it until it's hand tight and then just enough in order to make the connection that you need, but never more than 1.5 times turns past hand tight. Shear shaft on gear pumps, the reason why the shear shaft could break, 2 reasons. seepage drains used on pumps, the purpose of them. Operation of a bent axis piston pump, the conventions that are used with it. Operation of variable displacement pumps, particularly the operation of the compensator that's used with the different types of pumps. Ram air turbine, purpose of it. Purpose of the power transfer unit, PTU. Most of you will do okay, I think. I hope you will. Filters. Know a little bit about that. Differential pressure indicators. Different types of filter elements, centered elements, or maybe even a coil filter might be used on really old airplanes. Okay. I've given you what I can. I hope I've prepped you. The rest is up to you. You know, it's I'll do what I can, but you're going to have to help yourself as well. So study a little bit. I think you'll do okay. Any questions? Anything at all? Okay. All right. I'll see you out in the shop in just a few.